Self-induction. Self-induction. We look at the circuit. You have resistance can be changed. Change the resistor so it can change current. Okay, this is a solenoid, a coil. Okay, so a current established in this circuit. An induced electromotive EL appears in any coil in which the current is changing. If we change R, change I, then we have induced electromotive force produced in this coil. This process is called self-induction, and the electromotive force that appears is called self-induced electromotive force. It obeys Faraday's law of induction, just as other induced electromotive force do. Faraday's law of induction plus inductance. This is Faraday's induction law, and this is inductance. When inductance is defined by N phi over I, this is N phi. So we put N phi here equal to Li, then epsilon L equal to minus L di dt. Okay. Thus, in any inductor, such as coil, solenoid, or toroid, a self-induced electromotive force appears whenever the current changes with time. The magnitude of the current has no influence on the magnitude of the induced electromotive force. Only the rate of change of the current counts. Well, look at this picture. If the current increases, and then we have self-inductance electromotive force equal minus LDC. We see if current here, we have induced against it change. So we have this electromotive, this is negative relative to this point. Okay. Otherwise, if the current reduces, then we have induced against the change. You have current here. So this is, in this case, this is positive, this is negative. Okay. The direction of a self-inductance electromotive force can be found from Lenz's law. The self-induced electromotive force acts to oppose the change that brings it about. The polarity of a self-induced electromotive force is then the potential after the coil comparing that before the coil. The potential after the current compared before the coil. In this case, it's negative. In this case, it's positive. Okay. Let me read again. The polarity of self-induced electromotive force is the potential after the coil comparing that before the coil. If you go along the direction of the current, this is the direction. In any case, it's direction of current.
This power supply puts out about 6 volts. When we touch the output leads together and separate them, no spark is seen. If we hook the leads to this solenoid coil with 2,000 turns of wire and disconnect one wire, a small spark is seen. When an iron core is inserted into the coil and the sequence is repeated, a larger spark is seen.
We'll use this inductor coil and a light bulb to show the effect of inductance on an alternating current. When the lamp and inductor are hooked in series to 110 volts AC, the lamp lights normally at first. If we increase the inductance of the coil by inserting an iron core, the lamp dims as the core is inserted into the coil. The current flowing through the circuit has decreased.